Good morning, everybody. It looks like we've got a couple of people with a unstable connection. They keep on appearing and disappearing off the list. We'll get started. Welcome to this morning's webinar on the Pawnee fatigue saga. This is identical to the presentation I gave last night, my time, just for a catering for the audiences in different time zones. Last night went very well. We had an international audience with people from New Zealand, the UK, Finland that I could identify in the list. We've got a reasonable amount to get through today. It took me 90 minutes last night. We'll see how we go today. If you've got any questions, you can either type them into the chat, or if you click on the raise hand icon on your menu bar, it'll pop up and I can then unmute your microphone and you can then ask me directly by voice. So this morning I will cover a little bit of the history of the Pawnee and understanding the design. I'll talk briefly about a couple of the Pawnee accidents, in particular the accident in Colombia, which triggered the issue of the AD. A brief update on the current inspections worldwide, some of the problems that have been found, and then get into my calculations on the fatigue life. Are we inspecting the right areas? Moving into the efforts we've made in getting away from eddy current and using visual detection methods, an outline of my proposed future inspection regime, some of the limitations, and some of the other Pawnee work I've been doing. So in the beginning, the aircraft dates back into the early 1950s. In 1953, Fred Week at Texas University was engaged by Piper to design an agricultural aircraft using as many existing components from the Super Cub and the Tri-Pacer as possible. This was the intention to keep the aircraft simple and keep it cheap. Up until this point, there were no really dedicated agricultural aircraft designs, and people were using ex-World War II or pre-World War II aircraft that had been converted from the military. The aircraft was designed to meet the regulations that were in force at the time, and this was the US Civil Air Regulations Part 3. It's important to note that at that time in the world, fracture mechanics and fatigue in metal was not very well understood. Fracture mechanics is a relatively new engineering discipline, and there is no requirement in the civil air regs at that time to do any kind of fatigue analysis or put a life limitation on components or the airframe. The prototype aircraft first flew in late November 1954. There's a bit of a gap there until 1957 when production kicked off. And at the time, the maximum takeoff weight of the first design was 2,300 pounds. And the way you can visually identify the lighter weight Pawnees from the heavier weight Pawnees is the number of jury struts. The aircraft I refer to as the Pawnee A model has a single jury strut, whereas the Pawnee Bs, Cs and Ds have two jury struts. In 1964, they upgraded the Pawnee B with the higher horsepower engine and the increased max takeoff weight to 2,900 pounds. This was shortly followed by the Pawnee C and then subsequently by the Pawnee D. And the Pawnee D has the fuel tanks in the wings just outboard of the strut connection. By the 1980s, the type production and sales was winding down. Other purpose-designed aircraft were taking over, particularly aircraft that had a much higher payload. The type design was sold to the Latino Americana de Aviación in Argentina, and this is the company that's referred to as Lavia SA, who now hold the type certificate and are doing production in Argentina. One of the questions I get commonly asked is, why haven't we seen an AD on the Super Cub since it has an identical wing? The primary reason is the location of the wing on the fuselage. With the lift on a high mounted wing, you ended up producing tension in the strut. If you imagine that the strut is pivoted on the corners of the fuselage, as the wing lifts the strut up, it wants to try and rotate around those pivots and fold in towards the fuselage. This is putting a pressure inwards on the inner wing. This compression adds up with the compression from the local bending to form what we call a compression critical structure. If the structure were to fail under normal conditions, it would fail from the crushing of the spar cap, from the combined compression from the strut reaction and the bending from the local air loads. As you would expect, compression critical wings will have very low tension stresses because the tension from the local bending from the air loads gets countered by the compression from the strut reaction. And you end up having a very good fatigue life as a result. In contrast, you have the Pawnee design with the low mounted wing producing compression in the strut. And again, imagining that the strut has a pivot where it joins onto the fuselage. As the strut tries to lift up, it is pulling outwards on the wing. So you're getting a tension on the inner wing from the strut reaction. This adds up with the local bending from the air loads, and you get what's referred to as a tension critical structure there for the spar. This means that the spar will fail from tearing of the spar cap. As a result, tension critical wings will have very high tension stresses at the corner of the envelope and therefore have quite a poor fatigue life in comparison to structures that are compression critical. So looking at the development of the aircraft from the Super Cub and the Tri-Pacer, the Super Cub's got a 35-foot and a bit wingspan, a maximum takeoff weight of 1,750 pounds. With the Tri-Pacer, they increased the max takeoff weight to 1,900 pounds, but they did that by shortening the wingspan. And that decreases the amount of bending on the wing. So it was a very simple analysis to say, well, we shortened the wing, decreased the bending, therefore we can increase the max takeoff weight. With the Pawnee A, it's the same wing as the Super Cub. However, it's got the wider fuselage, so you have a slightly wider wingspan, but a much greater max takeoff weight, 2,300 pounds. I do have a copy or extract of the structural analysis used by Piper for the Pawnee A, and it's a very simple structural analysis with still quite a bit of margin there to be played with at 2,300 pound. However, with the Pawnee B, C and D increasing the max takeoff weight to 2,900 pound, Piper really sharpened the pencil to increase the payload capacity of the aircraft, and there's very little margin in the design. It's operating at its peak of its structural capacity there at 2,900 pound. There's what I consider a potential design flaw with the heavyweight Pawnees. The book value, nominal empty weight, is 1,530 pounds. Loaded with fuel, a mature girth pilot, and 150 gallons in the hopper, it brings the takeoff weight to 3,205 pounds. So you're 300 pounds over the max takeoff weight. If you are operating with superphosphate in the hopper, superphosphate can have a higher density than water depending on how fine it's being crushed, if it's a powder or a very granular product. And so you can overload it even further there with the superphosphate in the hopper. It's quite likely that the majority of the Australian Pawnee fleet were regularly operated over the max weight by agricultural operators. Um, I understand it was pretty common practice for economic reasons. Now, CASA did issue an airworthiness bulletin that allowed the operation of agricultural aircraft beyond the max takeoff weight on the proviso that there was a fatigue analysis done on the structure. Um, I'm not aware of any fatigue analysis having been done previously on the Pawnee, but I get the impression that the airworthiness bulletin from CASA tended to greenlight a lot of operators into operating beyond the max takeoff weight on a regular basis. Now, there was a crash relatively recently in Australia of a Pawnee. It had been fitted with the Fat Man wings from the GA200. And the ATSB could not conclusively prove, but strongly suspected that the aircraft had been overloaded and did not have the performance to take off in the distance that was available to it. So the stresses in the wing are very dependent on the weight of non-flying parts. Lower weight in the fuselage will result in lower wing stresses. So without weight in the hopper, you've got 33% less weight in the fuselage, and that results into pretty close 33% less wing stress for the same vertical G load, which in aircraft design terms we refer to as NZ. It's not quite linear due to the washout on the wings, and it changes the wing loading very slightly span-wise. It's important to remember that the agricultural aircraft are only carting the payload for half the duration of the flight. So it flies out heavy, comes back light, whereas we are operating at the lightweight all the time as glider tugs. So the Pawnee accidents, there are three mentioned in the AD from ANAC. There was two in Argentina. I have contacted ANAC in Argentina for further information on those accidents, and I have yet to receive a reply. There was an accident in July in 2022 in Colombia, and there was quite a detailed accident report produced by the Colombian airworthiness authorities, and I've done a rough translation of that accident report and sent it out to people. So this was the accident in Colombia. It was a crop spraying operation. The aircraft was in a descent over an obstacle. During the pullout from clearing the obstacle, the right-hand wing parted company with the aircraft. The aircraft spiraled into the ground and tumbled into a tree, inverted, and caught fire. Now, the pilot was fortunate to have survived the impact and was able to extricate himself from the wreckage prior to the fire burning out the aircraft. The crack occurred just outside of the hard walk area on the right-hand wing. It was traced to a badly drilled screw hole that had penetrated the corner of the spar cap and the flange and angled up into the channel there. I did ask the authorities if they had better photos available for this presentation, and the Colombians replied that only the report was the only information they had released. The screw hole where it penetrated the corner of the spar cap resulted in a crack. That crack had severed the entire flange. It had severed the spar cap and the opposite flange and had grown up the spar web to about the point where the white arrow is on the centre photo on the right-hand side before the fracture of the spar occurred. The amount of material remaining beneath the screw hole in the spar cap was probably aluminium foil thickness, and that probably split as soon as the screw was inserted into the spar, by my reckoning. The accident report from Columbia recommended that Levier SA publish guidance on where holes could be drilled in the flanges and recommended having an AD. That was in the initial report, and it's noted in the final accident report that Levier SA had since issued guidance in terms of a service bulletin and an AD as a result of the accident report from Columbia. This is the AD that we know and love. It has requirements for inspections based on calendar age of the aircraft, and for the aircraft over 40 years old, which is primarily the Piper-built aircraft, you have the eddy current inspection every 100 hours or 1 year. EASA have issued their own variation of the AD. The primary difference is for aircraft that are limited to 1,000 kilos or 2,205 pounds and placarded as such, the interval has been extended to 1,000 hours or every 4 years. Now, the UK the UK British Gliding Association has applied for an exemption from the ANAC AD and used the EASA AD. And that is for a listed number of aircraft that are being used as tow planes so that they are getting it inspected visually every 100 hours or 1 year and having the eddy current every 1,000 hours and 4 years. The New Zealand gliding has applied for something similar. They're awaiting a decision from the New Zealand CAA, and that involves getting the EASA substantiation. To the best of my knowledge, the EASA substantiation is based on a bit of that looks about right. They have some confidence that what they've done is appropriate. However, it doesn't appear to have been based on any engineering rationalisation in terms of calculation and fatigue life. In the USA, the Soaring Society of America responded to the proposed AD from the FAA, which came out in December last year. They've put in a fairly sizable response to that proposed AD, and they propose to carry out visual inspections using an inspection camera every 1,000 hours. We're not expecting a response from the FAA until about August or September. And it now looks that it's very apparent that Levier SA is waiting for that response from the FAA before doing anything further. So there are a lot of problems that were with the AD initially. The service bulletin that it required was originally only available in Spanish. It originally did not include the eddy current procedure, and it was written around the Argentine-built wing configuration, and the difference there is that there is a reinforcing strap under where the strut is connected onto the spar. And on the Argentine aircraft, it is on the forward side of the spar. On the Piper-built aircraft, it's on the aft face of the spar. As a result, the eddy current inspection could not be carried out on the Piper-built aircraft in the way that the inspection was written. Ben Tyrrell and myself took a fair bit of time to go and put together an AMOC, which were for an alternate eddy current procedure where we inspect the exterior of the spar flange rather than the interior. It is important to note that you need to follow the approved procedures and not get too creative and do your own interpretation on the intent of the AD. In particular, if it all goes wrong, you've got zero defence if you've gone and performed your own unapproved variation on the AD. So the problems found, almost all of it has been holes that have been either too close to the edge of the spar cap or the reinforced edge of the flange, which I refer to as the bulb. Holes that are too close to each other is very common, and this has been predominantly from the leading edge skin replacement. And there has appeared to be a couple of spar repairs, not spar, rib repairs to the spar where they've done something similar to this. We've only had 2 instances of corrosion in Australia that have been reported. Interestingly, they were both on the rear spar and in almost identical locations. Now, we were successful in getting 2 approvals by CASA for aircraft to continue operation with holes that are outside of the limits specified in the AD. These are for number 4 screw holes. They have greater than 1/4 inch separation, that is from centre to centre, and we can demonstrate that they have no fatigue impact. One of the requirements of those AMOCs is the holes shouldn't be left open. There is a fatigue benefit from having the hole filled with a screw. The fatigue life is calculated using what we call fatigue spectra. This is effectively how many times a particular G load occurs per flying hour. And you calculate this for the manoeuvre, the gust, landing, taxi, and the ground air ground cycle. The manoeuvre and gust is often joined together into the one spectrum. And the resultant life is you calculate the life for all of those components and add it together to get a final overall fatigue life. As I said before, fracture mechanics and fatigue in aircraft is a relatively new engineering discipline that really took off in the 1960s into the early 1970s. And at the time, Australian airworthiness authorities were collecting fatigue spectrum data on a wide range of aircraft, and that includes agricultural aircraft in Australia. But they also included 2 glider towing aircraft. One was a Super Cub being operated at Bacchus Marsh by the Victorian Motorless Flight Group. They clocked up nearly 1,000 hours of data in 2.5 years, so that's about 400 hours per year. I'm pretty sure there'd be plenty of club treasurers being very happy if they were doing 400 hours per year in their tow planes at the moment. And the other was an A model Piper Pawnee. It was a PA-25-150, but had been re-engined with a 180 horse motor. It was operating at Benalla with the Gliding Club of Victoria. It was probably doing the same hourly rate per year as the Super Cub. Now, the original data was recorded on paper, and when it was scanned into a PDF by CASA, they used an automatic page feeder, and there was a little bit of data where there was a misfeed and there was an overlap of pages. So we lost a little bit of the Pawnee data, but it's not significant enough to be an issue. And the similarity with the Super Cub data is just we've merged it all into one. So we have 1,500 hours of gust manoeuvre data for glider towing. We're really fortunate that CASA staff scanned and retained this data. As I understand, it was found in the bottom drawer of someone's desk during a office move, and they decided to scan it and keep it. To the best of my knowledge, it is the only known fatigue spectrum data for glider towing available in the world. This is what it looks like. You've got the spectrum chart on the left. You've got the number of exceedances per hour. It's a logarithmic axis. And on the vertical axis, you have the vertical G load. 1G is straight and level, and then you have 2G, 3G, etc. The blue line is the agricultural spectrum from the USA, out of an FAA document AC 2313A. There is a similar spectrum available for Australian agricultural aircraft, which is published in a document referred to as SM75. It's very similar shape to the curve. The the Australian data is slightly more benign, a little less exceedance per hour for the same G load than the what's published in the American data. The dotted green line is the single-engined private use from the American data. I've labelled it general aviation. And the orange line is the glider towing data. It's slightly more severe than the general aviation, the single-engined private use, and it's simply because we're doing nearly 8 flights per hour towing as opposed to an average flight of 40 minutes or so that's in the single-engined private use data. So we're doing a lot more circuits, a lot more general manoeuvring than what is being done in your typical general aviation aircraft. So, however, compared to agricultural usage, if you look at the 2G line, glider towing, you're encountering 2G a bit over once per hour, so 1.6 times per hour. That would be in the order of doing a gentle turn and flying to a thermal and getting the surge from the thermal, pushing you up to 2G briefly. However, with an agricultural aircraft, you're looking at about 40 times per hour. So you can see that it's about 20 times worse for an agricultural aircraft than for a glider towing aircraft. When I ran through the numbers, the fatigue life is being driven by the ground air ground cycle. So if you imagine the wings being bent up when it's flying, wings on the ground at rest or when it's maneuvering on the ground, taxiing, and then back when it's flying and bending up. That's the cycle that's driving it. The chart on the left is similar to the previous chart, except it's now the number of exceedances per flight. And that means our positive wing bending is in the order of 1.7 G once per flight, compared to 2.4 G for the agricultural aircraft. Important thing to note is the agricultural aircraft in Australia were doing up to 9 flights per hour. This reflected the Pawnee flying to a farmer's airstrip or a suitable paddock, loading up with the super or the pesticide, fence hopping across a couple of paddocks, doing the application, fence hopping back, reloading and going again. Whereas in the USA, they were operating out of a regional airport, transiting to the application area, doing the high G maneuvers and transiting back. So there's that transit is at 1G. It's not doing much in the way of maneuvering during that time. So it's reasonable to expect that we could actually base the inspections not on flying hours but on landings, because with the agricultural aircraft you're doing a certain number of high G manoeuvres per flight, and with the glider towing is pretty much doing the same thing time and time again, towing up to 2,000 feet AGL, dumping the glider, returning. With the change in the operating weight and the difference in the vertical, the NZ, the G per flight, we've ended up with a stress reduction nearly 40% compared to agricultural aircraft. The compressive stress state for the ground part of the cycle comes from the taxi phase. The agricultural aircraft have a unique taxi spectrum. The tow plane spectrum for single-engined general aviation dates back to a military specification from the USA from 1960. It's most likely for sealed runways. It is most likely to refer to taxiing the aircraft from the apron out to the launch point or the runway, and then from the runway back to the apron. With glider towing, we would be landing the tow plane, turning around, going back to the launch point, hooking up the next glider, going again. So our amount of taxiing we're doing is a lot less per landing than what would be expected out of the spectrum that I've used. The mil spec does say that if you're operating from rough surfaces to double the number of exceedances per landing than what's specified. My estimate at the moment is that we are conservative. We're doing a lot less taxing, even though we might be operating off grass or rougher surfaces, and that it's going to balance out a little bit there. However, a potential line of future work would be to go and record what a taxi spectrum would be for gliding towing operations to see if it makes any difference to our fatigue outcomes. This is what the stresses look like along the span of the wing. The lower spar caps on the upper chart and the upper spar caps on the lower chart. I should have reversed those around. The worst case for glider towing occurs at the wing root immediately outboard of where the wing root fittings are. I've noted where the Columbia failure occurred on the lower spar cap chart there. The R ratio is referring to a stress ratio, or the ratio between the compression stress and the tension stress. With fracture mechanics, the more you compress the crack tip and then open up again, the shorter the fatigue life will be, or the faster the crack will grow. So having a stress ratio near zero or even positive is a fatigue benefit. You'll note that the area under the strut attachment and the area mid-span on the upper spar cap between the strut and the root are similar stresses and a similar stress ratio, but significantly lower than what's happening at the root end. With agricultural usage, the higher G loads load up the outer wing a little bit more. As a result, the stresses under the strut and in the mid-span region there are higher and are close to what is occurring at the wing root. So there's not too much difference fatigue-wise between those areas. But because we are operating the aircraft far more gently, we have quite a difference between what's happening under the strut, mid-span, and then at the wing root, to the point where some very rough numbers suggest that inspections at the strut and mid-span should be about 3 times less frequent than what's happening at the wing root. So fatigue life calculation is very sensitive to small changes in inputs. It's normally backed up with material coupon tests, in-flight measurements of loads. It's worth pointing out that my stress analysis there is purely based on theoretics, based on the design of the wing and expected flight loads. It would be great to actually measure things in flight just to verify that what I've done is close to what's actually occurring on the aircraft. And certainly for larger aircraft, military aircraft, we get a full-scale fatigue test. And the photo on the right is of the A380 undergoing fatigue testing and showing the range of movement between the wing at rest and the wing in flight in the whiffle tree there. The fatigue life calculation has 2 phases. You've got crack initiation and crack growth. The first phase is where you're forming a proto-crack at a microscopic level. Challenging to calculate because there's a lot of scatter, a lot of noise in the data, and it's very sensitive to very small defects at the micro level in the metal. One of the things that is a major issue is we have next to no data available on the thread forming screws and what their impact is on crack initiation. Thread forming screws are not used in fatigue critical areas typically. This is a very unusual aircraft as a result of that. One of the things we are doing is we are deforming the metal as we are putting these screws in initially. That is cold working the metal. It's changing the material properties, and the extent by which the material properties are changed will change the fatigue properties in that immediate area around the screw. There is some research to say that as you install the screw, some of the metal is being sheared along with the screw thread and then being pushed in towards the shank of the screw. As this happens, you are then compressing the metal outwards less. So the amount of metal that's being compressed outwards is then going to be a bit of a trade-off with how much metal is being sheared along with the thread into the shank of the hole. And that's going to have an impact on the fatigue properties. So because I have an unknown there, the current calculations I've done, I've used a much higher stress at the hole than what's occurring in real life to be conservative. I've also used a much larger hole in the fatigue calculations than what is present to account for the diameter of the thread. In early March this year, I was picked up two master's students at Adelaide University, and they're starting some coupon testing. Now they're going to be using 6061 T6 sheet in lieu of extrusion. That was just a time factor. Getting a suitable length of extrusion was going to take too much time for what we had available. They are going to be performing 3 sets of tests. One is samples with a smooth round hole. That's our control batch. We have enough information on fatigue originating at round holes to be able to predict what's going to happen there. We're going to test some samples with the thread forming screws fitted, and then we're going to have some samples where we fitted the screws and then remove them. So we have the edge of the thread, the cold working of the hole, but the screw removed. And these are going to be tested under a constant amplitude stress cycle that reflects the ground air ground cycle. And we're expecting to get the results later this year. Given suitable students next year, we might try for extrusion and potentially develop a life stress curve or stress life curve. So when we get those results, I'm going to use them and compare the data from the smooth holes and the data from the screws that have been removed to try and determine what the effective stress concentration around the hole is. And that will account for some of the cold working as well. Typically for a round hole, you'd use 3, but we've got a jagged edge from a thread in there oblique to the applied stress. So the trade-off there is going to be how much benefit do we get from the cold working versus how much pain we get from having the jagged edge in the hole from the thread. The second batch of things I'll do is compare the results from the screws fitted and the screws removed to determine what's referred to as a hole filling factor, what benefit we get from having the screw in the hole. On the right is a table out of an engineering design textbook. I'm currently using a factor of 0.9 in my fatigue calculations, and that's worst case for a threaded bolt. We might be able to get a much better benefit because these screws are an interference fit. They're very tight in the holes. I just don't know how much benefit we're going to get out of that. So this may improve the fatigue calculations a bit, or at the very least, validate the current assumptions that I've done. The second phase is crack growth. After initiation, you assume to have a proto crack in the order of 1/4 of a millimetre or 10,000ths of an inch. The area around the screw that is being stretched but not enough to deform the metal, provides a donut-type ring of residual tension. As the crack grows and gets into that area where there's residual tension field, it's going to accelerate briefly as it grows through that area. Once the crack exceeds that area, it's going to behave quite predictably. Again, I've used a much higher stress around the hole in my current fatigue calculations to account for that residual tension. Now, the residual tension will depend very much on how much metal is being pushed outwards in the deformed area and how much of the metal is being sheared in along with the screw thread. I've currently used what I consider a worst case stress, and it's the stress that is correct for the late stage crack as the crack is growing along the spar cap. Again, the results from the uni students will help validate whether that assumption is really good or whether I need to change the calculations there. At the present time, the calculations I've done for agricultural use, if it's operated within the aircraft limits of 2,900 pounds, has a fatigue life for 7,800 hours. That's the point at which initiation has happened and you should now expect to see cracks occurring. And 8,000 hours is not a bad round number for agricultural aircraft, and it's comparable to other types of aircraft doing agricultural work. So it's not a bad result. If you're operating the aircraft over max takeoff weight, that's very punishing on the structure, and it reduces the fatigue life to 3,300 hours. I did do some numbers earlier on for what happens if you have a screw hole that damages the edge of the flange, so it goes through that reinforcing bulb, and that halves the fatigue life again. So you could potentially have an aircraft, if it's got a hole in the flange at the wing root and being operated beyond max takeoff weight, with a fatigue life in the order of 1,600 hours, something like that. For glider tow plane up to that 1,000 kilo limit, or 2,205 pounds, it's 1.5 million flying hours. So that's if you've got brand new spars and have only done glider towing. And even if some of my assumptions are not so great and you divide that by a factor of 5 just to be safe, you've got 300,000 hours. So even if you're doing 300 hours a year, you've got 1,000 years of flying out of brand new spars and only doing glider towing. The inspection intervals using eddy current, again, agricultural use up to the max takeoff weight, is every 200 hours. Once you get a crack growing in an agricultural aircraft, it'll grow quite quickly. And for beyond max takeoff weight, it's 150 hours. Current calculations using eddy current for glider tow planes, 2,100 hours. Now, having done all that, I've since been asked to look at what can we do to get rid of the eddy current? Can we go and do visual inspections on the aircraft instead? And that changes the numbers a little bit because the detectable crack size for visual inspection is going to be longer. This is just a visual representation of where we're at in terms of the fatigue threshold. So this is the end of the initiation phase where you now have detectable cracks in the structure. On the left-hand side is that ground air ground vertical G and the takeoff weight. That's just a measure of how heavy you're operating the aircraft and how much you're throwing it around. And you've got the agricultural use on the left. The life is in hours along the bottom. Again, it's a logarithmic line, and there's 2 dots there for tow plane usage. The lower one is for operating at 2,205 pounds, and in Australia we've got a number of Pawnees that have been converted to a side-by-side two-seat configuration. They operate at a higher operating weight with two pilots on board, and that's what the higher dot represents. And as you can see, we're on a very flat part of the curve, so that any minor reduction in stresses gives us a very big increase in that fatigue threshold. This is the inspection interval, similar chart with the G load and takeoff weight on the left-hand side and the interval in hours along the logarithmic line on the bottom. The two dots on the tow plane there again reflect the 1,000 kilos, 2,205 pounds on the bottom, and the two-seat usage higher up. So the big question I have is, are we inspecting the right areas? The current inspections seem to be focused on previous history of leading edge screw holes with close proximity holes, either close to the edges or close to each other holes, leading to premature cracking. And this is based around leading edge screws being removed more frequently due to leading to damage around the holes. The wing root area hasn't been covered because it's got that leading edge extension over the outside, which seems to shield the leading edge, and therefore you might have less damage occurring in that area. But one of the problems that I have with the current inspections is that the AD states that close proximity holes are unairworthy and they cause premature cracking. So what we really need is an inspection procedure and an interval for normal holes, holes that are allowed for in the design. So in the inspection areas, there are other normal holes nearby that are not currently being inspected. And these are the screws that secure the ribs to the flanges on the spars. They're identical screws. They're exposed to the same stresses and the stress cycles, and these might also develop cracks. On the good side, these holes are drilled with a jig in order to match the rib. There don't appear to be any holes close to the edges as a result. Ribs are less likely to be damaged and then been removed and refitted, and so you end up with less likely to have multiple holes or just damage to the screw hole. The major ribs have 4 screws. There's 2 in the front of the spar and 2 at the rear of the spar. The intermediate rib on the leading edge has 2 screws into the front of the spar, as per the original design. There are some aircraft out there with aftermarket supplemental type certificate approved ribs, which are a pressed sheet metal that are attached onto the web of the spar by rivets. This is not what I'm dealing with here. As a result, we will need to access the front of the spar to have a look at these screws, which is going to be a challenge. So my recommended inspection areas for tow planes at the moment is we need to have a look at the lower spar caps at the wing root. These are not currently inspected. They are the highest cyclic stress area on the airframe in tow plane use. It's where the Columbia accident occurred, and there was previously an FAA AD back in the early 1970s that required inspection of the holes for the J stringer at the bottom of the wing there. And that was every 300 hours until the wing root doubler was replaced. And that doubler was originally a triangular piece of metal. The replacement one had 2 long tangs added to it, one running up along the upper side of the spar and one running along the lower side of the spar. The stresses, as I showed earlier on, for the current inspection areas, which are in the mid-span between the root and the strut and under the strut, for glider towing could probably be pushed out to every 6,000 hours with eddy current. So are the cracks reliably visually detectable? And the answer is maybe. When we look at NDT inspection methods, we look around the probability of detection of the method to be used, and visual inspection is typically the least reliable inspection method. Eddy current can typically pick up a 50 thou or 1 1/4 millimeter crack with a 90% success rate, which is what's shown on the chart on the right hand side. So the crack size is in millimeters. 1 1/4 millimeters gets you that 90% probability. So if you were to do an initial inspection followed by 3 more inspections, you would have a 90% chance of picking up the crack initially. The second time around, you would have a 90% chance of picking up the 10% that were missed before. So you're now at a cumulative 99%. And on the third time, you have a 90% chance of picking up the 1% you've missed. So you're at a 99.9% chance of picking up a crack. If you were to look at visual inspection methods, the dotted line there comes from some Boeing data. That suggests we should be able to pick up a 7.5 millimeter crack with 10 times visual magnification. We could play a few games there and say, well, if we wanted to try and pick up a 5.5 millimeter crack, that's around 67% reliability. We'd need to inspect twice as often. So the first inspection would be 67%. The next inspection would be picking up a 67% chance of the 33% we missed. So you're then at a 89% chance, which is close enough to the 90%. So you could then work out more frequent inspections to pick up a lower probability chance of a crack that way. However, the big problem with visual inspection is whether the crack is actually open or closed. If it's a very tight crack, you might not be able to see it. And using these inspection cameras, the critical factor is more likely going to be, is the crack wide enough to occupy 1 pixel to be visible on the screen? So on the ground, cracks might be pushed closed by the weight of the wing. I did a fair bit of work on the P3 Orions back in the day, and there was an instance there where we had to demonstrate for an inspection that there was sufficient bending being applied to the wing to hold the crack open to make it more easily detectable. The way around that is we might need to apply a little bit of force under the front spar to open the crack to make it more visible. The alternative is relying on the residual stress around the screw. Now we have a bit of a trade-off happening. The photo on the right is from an inspection camera that was purchased by the Soaring Society of America, of the inside of the flange. And you can see there that the orientation of the camera relative to the screw, the tail of the screw protruding into the field of view might obstruct the view of the crack on one side. So any visual inspection will need to move the camera around a bit to ensure that you've got good visibility of both sides of the screw. However, with the screw fitted to the hole, we should be seeing some kind of residual tension in a ring around the hole, and that any crack that forms may be held open by that residual tension field. So one of the things I hope to achieve with the master's students at Adelaide University, once they start doing their coupon testing, is when they start getting cracks developing in their coupons, just to pause the testing and do some visual inspection using inspection cameras and the macro lens on my camera to see if the cracks are being held open by the screws without any load being applied on the coupon. And that will help be some of my proof to CASA that we can detect these cracks that way. We also have the crack-like indication on an aircraft at Narromine. I hope to be able to get an inspection camera and use that on that aircraft to see if it really is a crack at that hole, and if it is a crack, then whether or not we can insert a screw into that hole and see if that forces the crack open or not, and we can visually detect it that way. The ability of the inspection camera to detect cracks is going to be very dependent on the quality of the optics and the camera resolution. Now, we've got very small area that we're working in, and the camera resolution is going to be very limited by the diameter of the optic head. We're looking at around 3 mm diameter optic head to allow to get the camera inside the area and have adequate view of the holes. A cheap inspection camera with lower quality lens might not detect cracks well. We'll look at specifying either a minimum camera resolution and diameter, or most likely what will happen is Gliding Australia will purchase a number of high quality inspection cameras for this purpose and have them based in the regions to be hired by operators. It's worth noting, again, this is another photo on the right-hand side from the Soil Society of America and their trials with inspection cameras. It's a 400 by 400 sensor on this particular image. You can see that where the arrow indicates is where the thread has broken through on the inside of the flange, and there is a bow wave of material either side of that, that is the material that's been sheared along with the thread as the thread's been formed in the hole, that's been displaced inwards. That notch in that bow wave is probably large enough to be picked up by eddy current as being a crack-like indication, and that would be a false alarm. So one of the things I want to look at this aircraft in Narromine is whether we do have a bow wave kind of feature like that giving us a false alarm or not. Now, I did do some trials with a 3 mm direct view camera. This has a minimum focus distance of 8 mm. It results with an effective magnification of around 9 times using the screen. And I could demonstrate that it could easily detect features down to 60 microns or better. I do have a sample of aluminium with stress corrosion cracking, and so I could prove that it was capable of picking up cracks in the aluminium, and that's the top photo on the left. It's a little small on the screen, but I could easily see that there was a 2 mm crack at the bottom there. So we're down into the 2 mm crack length range, but with stress corrosion cracking, the corrosion product that's inside the crack is wedging the crack open. When I tested this camera on a Pawnee sample, it was not as good as I'd hoped. The closest I could get is with the 8 mm focus distance is shown on the left hand side, and it does not give us an adequate enough view of the face of the flange to determine whether there's cracking or not. I did send a sample of flange of the spar cap to a camera manufacturer in China. That was Kunscope, and I had very good assistance from the sales agent there, Mirror. And she was able to get a example side view probe. So this is where the lens is mounted on the side of the fiber optic, and demonstrate that we could get reasonable view with a 720 by 720 sensor. So the good chance that we're going to be able to achieve crack detection using this technique. On the photo on the left, you can see there's a bit of corrosion occurring around the edge of the hole there. You've got the discoloration suggesting a bit of intergranular, and there's some flaking there, maybe a little bit of exfoliation. There's a lot of dirt and crud that collects in these channels as well. The diagram on the right-hand side is just an indication of the somewhat claustrophobic area that we're trying to get a visual inspection camera into. So the sample I sent to China was from near the wing root, and this is the lower channel on the lower spar cap. The spars had collected a lot of dirt and crud, and so we're going to end up needing a cleaning procedure to be carried out prior to any visual inspection to ensure that we've got adequate visibility of the surface to see if there's any, and so that the crud's not hiding any cracks if they're present. The section of spar that I have that was further outboard is a lot cleaner than the area that was sent in from inboard. So the proposed future inspections will be to use an inspection camera inside the channel. This is going to be the side view camera. We will need to install access panels into the lower surface of the leading edge for access to the front of the spar. Inspections will be in the order of 500 to 1,000 hours. That's going to need to be calculated yet. And we'll need to inspect both the rear and the front screw holes on the front spar, in particular at the wing root. We won't need to remove the screws, with the exception being at the aft face of the lower spar under the strut connection where that reinforcing strap is located. And we're going to need to inspect the outside face of the spar in that location. The inspection of the upper spar in the midspan and the lower spar under the strut will probably be in the order of 1/3 as often as the inspection of the wing root. So if we do end up inspecting the wing root, say every 1,000 hours, inspection of those outboard areas will be every 3,000 hours. And the proposal at the moment will have Gliding Australia purchase suitable inspection cameras for the regions. That doesn't mean that individuals can't go and purchase their own inspection cameras, but they will need to have reasonable quality optics and very good resolution. Now, the inspection cameras that I'm looking at the moment are in the order of $6,000 US. So at 10,000 Australian, it's unlikely that an individual or an individual club is going to be purchasing one of these straight off. So on my to-do list at the moment is I'm going to recalculate the stress analysis. I have some slight shift in the cross-section dimensions, which increases the spar area. That was going to reduce the stresses slightly. There was an assumption made in the earlier on about how much of the weight the front spar supports. I've now got the design information from New Zealand for the modification of retrofitting the fuel tanks into the wings for the B and C models. And they obviously had access to the Piper analysis for the D model wings. And that makes the assumption that 1/3 of the weight is being supported by the front spar and 2/3 by the rear spar. In my initial calculations, I had that the other way around. That weight distribution has been verified by one of the wings in Canberra. It is indeed less weight on the front spar than what I thought. That will change the stress analysis very slightly. It will end up reducing the stresses a little bit, and because we are on a fairly flat part of the curve there, that minor reduction in the stresses are going to increase the fatigue threshold and inspection intervals a fair bit. The determining the stress concentration, the filling factor, that's going to be resultant from the master student research. They'll have results later this year. I do need to make a decision in the not too distant future on the inspection camera. That's key to determining the inspection intervals by working out just how small a crack we can see. And I'd like to have it present so that when the university students start doing their coupon testing, I can look at the cracks being developed with that inspection camera. I have given a sample of the spar to Len Dykeman in New South Wales. He's going to have a look and see whether we can have any advanced optical techniques for crack detection there. I'll need to recalculate the fatigue analysis using the above data. I will also include the interval for the midspan and wing strut areas for glider towing. I won't bother to do it for the agricultural usage. It's not worth doing. Fair bit of work in there. I can get started on that once I've redone the stress analysis. I will need to get to a point where I need to wait for the university student research results to become available before I can complete that. With a bit of luck, I'll have that done by December. There's a few limitations to what I've done. I'm only looking at the spar flanges. We might get future issues, particularly in agricultural aircraft, arising from the 6 bolts for the wing root fitting. The mounting point of the wing is offset very low on the spar. That puts quite a moment into that 6 bolts of the wing root fitting. It produces quite high loads through those bolts. Something similar happens with the 6 holes that mount the strut onto the spar web. It's not quite so bad for tow plane use, but for agricultural use, I am anticipating there's some quite high loads through those 6 bolts. And it doesn't cover the first or the last rivet for the strap under the strut fitting. I haven't looked at any loads through that strap individual or the load transfer. Just eyeballing it, it looks like a potential hotspot, particularly for agricultural aircraft. So I am prepared for a possible future where agricultural aircraft have issues and we get further ADs, possibly in these areas. I haven't considered the rear spar at all. I can generate in-flight loads and stresses for there. I just haven't looked at it. It's quite highly loaded by the aileron and the flap loads. Whilst I've looked at the flap loads for the landing case, I have not considered anything for rolling design cases. It's worth noting that I joined the Air Force back in the late 80s, and by the mid-1980s, the Australian Air Force had found that they had different cracking patterns between the left and the right-hand wings of their Dassault Mirages as they were being phased out and replaced by the FA-18 Hornets. And that was because at that time, the fighter pilots always did the brake right, doing the hard roll right and pull onto the G for missile firing. So we ended up with quite asymmetric crack patterns in those aircraft. It won't be a problem for glider towing, but it is worth noting that we have a built-in bias because the tug always turns to the left after gliding release. So we do have a feature where we might have some asymmetry between fatigue on the left-hand wing and the right-hand wing because of that. In other work that I've done, the flight loads model that I've produced in Excel has given me very good information to look at the CASA AD number 36 Amendment 3 for the ring root fitting on the fuselage. We still have 8 Pawnees operating as tow planes that have not had the alternate fittings fitted to that area. We now have the fatigue spectra and very good load data. So I've done a stress analysis on that to say that if you're only doing glider towing, it's possible to increase the hours for the inspection interval from that 500 hours of 4,500 landings to 6,500 hours or 50,000 landings. For the single-seat aircraft, two of these aircraft have the two-seat conversion, and they can be re-inspected at 5,400 hours and 42,000 landings. That's now been submitted to a Part 21 engineer. It will come out with a maximum weight restriction being applied to the aircraft. They'll have a placard on the instrument panel and a flight manual amendment as part of the approval for this. Future work with the university students, we'll look at getting the larger size extrusion from maybe Wix. That comes with a 80 thou thick spar web. Now the flanges on these Pawnee spars are 90 thou thick, so we're in the right ballpark, and potentially look at producing a fatigue life versus max stress cycles kind of diagram for examples of that with the screw fitted as design data, something like that. I'll have a chat with the supervising university professor later this year about what we could potentially do with that. The other one would be to look at producing data to determine the variables used in the crack initiation equations and see if we can improve that calculation method there. And that's it from me. If you've got any questions, you can stick your hand up. I haven't seen anything come through on the chat yet, so there's either stunned silence or that. David, if you want to speak, you can click on your microphone icon at the menu bar to turn your microphone on.
Hi, are you able to hear me?
Yes, David.
Hey, okay. Well, hello from California. I really appreciate your report and all the work that you've done for doing this, and all of this is like really great. One of I guess my first question is kind of how much of the Australian Pawnee fleet has been inspected, either just visually or following the high frequency eddy current inspections that the Argentinians have kind of determined that need to be done? And two, have you actually found a crack from a hole that we would call airworthy, not in the bulb, not in the lower angled area, but a hole that you and I, as engineers, were considered okay for fatigue and not affecting the actual strength of the spar.
Okay.
And I'll just leave that.
All of the Pawnee fleet used as tow planes has been inspected using eddy current. That's 45 aircraft. We had around half of the aircraft grounded primarily due to the additional holes, so holes that are too close together or holes that are too close to the edges. Two of the aircraft that were grounded for corrosion on the rear spar. At least one of those aircraft is now flying again with a repair scheme from a Part 21 or an approved engineering organisation. We have had one crack indication on an aircraft. This is the aircraft that's at Narromine. It had an interesting history. The spars were supposed to have been replaced when it was rebuilt. And since it has been rebuilt, it has only done glider towing operations. But it looks like they used or recycled a second-hand spar from another Pawnee during the rebuild. That particular spar has one additional hole in it. It is some distance from other holes, so it is a hole that you would consider to be safe fatigue-wise. It had a broken screw stud in it, and it had a crack-like indication um, as a result of the eddy current being performed on the inside face of that flange. It is the only aircraft that I know of where we've had a crack-like indication. I want to get over to Narromine at some point with a suitable inspection camera to have a look up inside that gap and see if we can see what's going on there. I have had reports from overseas in Europe where people have had crack indications, but it's been swarf or bits of metal where the screw is broken through the inside face of the flange. And what they've done is used a bit of sandpaper, wet and dry, removed the grotty material on the inside of the flange there, and it's then come up as a clean indication they've passed the eddy current testing as a result of that. So we have one aircraft out of 45 that has had a crack-like indication, and we want to verify that in the future.
As a follow-up question, have you found any of your Pawnees with I'll just call it I call it the Swiss cheese condition, where it seems like it was very normal in South America to reskin the leading edges for whatever reason. I don't know why they were doing it, and it seems like multiple times in a short period, either bird strikes or hitting fence posts or crops or something where they needed to reskin. And this is kind of leading to what I view is not as a fatigue problem with the design and not meeting the type certificate of the airplane itself, but rather it's a maintenance problem where maintainers are not understanding that you just can't arbitrarily put screws on spar flanges, especially in corners or around bulbs, and severely affecting the fatigue life of the airplane. Not, much less, these airplanes are probably being operated outside of their approved envelopes as well. Have you found any with like the Swiss cheese, if you know what I mean, where it's 3 or 4 holes all very close to each other, where new screws were installed because they were just putting new leading edge skins on?
The problem with the Swiss cheese is it's a common problem worldwide. There was no guidance. I don't think there's a repair manual at all, actually, for the Pawnee. There's no guidance anywhere in the Pawnee documentation on where to drill these holes. The holes are being drilled blindly. If you have the leading edge skin folded over the flange, you can't see where the original hole is. And you're going, well, we'll just put the hole in somewhere about there. The guidance that came out with the AD about allowable screw positioning on the vertical positioning on the spar flange, in my opinion, is incorrect. As I said before, with the original CAR 3 certification, there was no requirement to do any kind of fatigue analysis whatsoever. And the guidance provided in the AD actually allows the screw to penetrate the bulb. My interpretation of that is that this is the original go no-go gauge that Piper used during production, and that what they were looking at was purely static strength. Is the screw going to shear out through the bulb as opposed to any kind of fatigue requirement? So my advice differs from what's been published in the AD in a couple of areas. I do not like the idea of screws penetrating that lipped edge on the flange at all. So back onto the question about the quality of repairs. We found quite a few aircraft with multiple holes close to each other, not necessarily as Swiss cheesy as some other examples that I've got photos of, but I think the photo that I showed on the slideshow came out of Europe. I've seen other examples from the USA and from Australia where you've got multiple holes in close proximity to each other. It's a worldwide issue. It's parked almost half of our aircraft as a result.
Is your fix for the Swiss cheese like that a complete respar, or have you been able to do local repairs and get that approved from, I hear it was like Part 20 or Part 21 as part of your local authority? I'm sorry for so
Uh,
many questions.
no,
Head
it's
away.
all good. The problem with the spar is the flange and the spar cap really a bit too small to get a decent sized rivet or high lock through it. I did get together a Part 21 engineer myself and another colleague who formerly worked at Airbus along with myself, and he actually came out of Pilatus. Um, we sat down and had a bit of a design team going about whether we could come up with a repair scheme suitable for these holes. We struggled. Um, we did look at the idea of a bonded repair, which is about the only way you could get a suitable repair onto the flange or the spar cap. Um, Not real keen on that with some of the agricultural history of the aircraft and the potential contamination on the spars. And it's very hard to get a good bond on a dirty surface. You need to get the surfaces really clean to get a reliable, strong bond. The repair scheme that we did suggest ended up having an L-shaped plate attached onto the spar web with the lip of the L um, moving up into under the cap. A very inefficient repair. The load transfer from the cap into that plate was very poor because it only had fasteners through the spar web. We did look at that one recently. We had an aircraft with additional holes outboard of the strut, so where there is a lot less bending going on. And we considered implementing that repair scheme and on that aircraft because we knew that the bending in that area was much less than further inboard, and we had some good margins on our structural calculations there. As it turned out, the aircraft subsequently found some more Swiss cheese further inboard, and they decided to scrap the spar and replace it. So at the moment, it only looks like it is spar replacement. I do note that Piper had a spar splice kit, considering of some splice plates attached onto the spar web, and that was for areas outboard of the strut. And that was going to be part of our substantiation, was that the Piper originally allowed spar splices to be carried out just using a spar web splice all the way outboard of the strut, and therefore our repair was going to be suitable. But I don't have any idea how we would repair inboard of the strut assembly, simply because the space available to get fasteners into the flange or the cap is just not there.
I agree with all of that. I don't think it's unreasonable for any regulatory authority to incur an inspection, and then if you find the Swiss cheese, then you just need to replace the spar as a one-time thing, and then based off your report, go, okay, if it's a new spar, then really you don't need to inspect it. I guess my last question, and allow others to speak. Again, thank you for allowing me to ask so many. When you said if you replace the spar, it's brand new, and you only use the aircraft for towing, you had some kind of million cycle idea
One
there,
one
but
and a
the,
half million flying hours. Yes, a long time.
a very long time, right? Almost, every glider by that time will be self-launching,
Yes.
and so that we won't have this tow problem, for better or worse. But you also stated that you needed to start doing 2,000 eddy current inspection with such a high life limit. Why the 2,000 hour eddy current inspection? Shouldn't that be more on the order of 100,000 flight hours? And so I just kind
Um,
of wanted to get some clarity on that.
yeah, the two different phases you've got is one is the initiation and the other one's the crack growth. Once you get a crack growing, you're in a different phase, different calculation method. And with glider towing, it will grow very slowly, any crack you have. It just takes a long time for it to initiate. And I had a lot of trouble actually getting cracking to initiate in the calculation model. The 2000 hour inspection using eddy current is primarily for aircraft that have got agricultural history on the spar. So these are not brand new spars. These are old spars that do not have Swiss cheese and continuing operations with glider towing. So instead of inspecting every 100 hours or 200 hours, it would be every 2000 hours. So in Australia, we're going to be ending up looking at having two fleets of Pawnees. Pawnees that have had spars replaced and do not need ongoing inspections for some considerable time, and Pawnees that are still have spars with agricultural hours on them and possible cracking. Therefore, they'll have ongoing inspections. If we get away from eddy current, the inspection interval will be shorter. I've yet to determine just how much shorter, but every 1,000 hours or slightly less is probably a reasonable guess at this point in time. Anything else, David?
Yeah, I guess my last question, because I think you and I will agree that this whole mess was started by the Argentinians releasing an AD, which I don't know. I don't think really addresses the risk to the airplane. Again, my stance is that this is a maintenance problem and not a design problem, in which these are old airplanes, and are just being flown beyond a life limit that wasn't accounted for the Car 3 certification. Um, what kind of relationship do you have with the Australian authorities? And are they listening to you, or are they just kind of playing the Mexican standoff with the Argentinians and potentially the United States waiting on whatever the FAA does?
The relationship with CASA, our regulatory authority, has been going fairly well. We had a few rocky moments initially. I was present at a meeting with myself and a Part 21 engineer who's also a glider pilot, and we presented the idea that the ongoing inspections were not required because the abnormal holes or the close proximity holes were being grounded, and that aircraft with normal holes did not require inspection. That meeting went downhill pretty rapidly, actually. Since then, the relationship's been rebuilt. They're sharing a lot of information with me. I'm sharing all the information I come up with them. The proof will be when we start submitting AMOCs for the aircraft that have agricultural hours on their spars, and seeing if we can get a suitable inspection increase using an alternate inspection method. So there's two factors involved there. One is the approval of the visual inspection techniques. The second is the extension to the interval based on how we are using the aircraft. Glider towing is very benign. Um, it really depends on how much damage has been done to the aircraft fatigue-wise in its previous life as an agricultural aircraft. I think in terms of the aircraft with new spars, I think it's going to be fairly straightforward to get approval of that we do not need to inspect for a very long time on those aircraft with new metal.
Can you explain further why the meeting went downhill, such as, I guess, what is the pushback from the AN, is it ANAC or the, I just want to say the Aussies. What was their reasons for pushing back on, because anybody who does any kind of fatigue analysis or has done metallic repairs of any level know that like whatever this has been proposed and released is not actually suitable for addressing the condition. And so I would think that there was people on that side of the table who could, if talking with your report, would see the rationality and the physics behind it versus the administration and like what has already been done. Does that make sense?
I understand where you're coming from, and you and I are certainly potentially on the same page. When we looked at the AD originally, we saw calendar-based inspection requirements, which is usually a red flag when you start talking about fatigue. This aircraft over 40 years routine requiring deeper inspection just didn't make sense to anybody who looked at it in detail. Whereas normally you would expect aircraft that have done it 2,000 hours or aircraft that have done 10,000 hours or something like that in a fatigue inspection kind of AD. So the first red flag was there. I won't speculate as to why CASA gave us the pushback, other that it got pretty heated, to say it mildly. And it took a little bit of work to rebuild that situation. We also had a problem where, because CASA had accepted the AD from ANAC and had said it was applicable to Australian Pawnees, and the eddy current procedure had not been published at that time, we would have been grounded because we could not carry out the required inspections. And there was a lot of discussion at quite high levels within CASA and Gliding Australia to try and work out a way around that. And we ended up with a workaround where visual inspections for additional holes were carried out until such time as the eddy current inspection requirements became published, and then we were required to do the eddy current inspections. So I won't speculate too much on why CASA gave us the pushback. We were in a situation where we managed not to get grounded, and we've had the eddy currents carried out. Not necessarily a bad thing. It forced people to look very thoroughly at the state of their spars and remove the Swiss cheese from the structure. And so there are some aircraft there that were Swiss cheese that maybe would have been better to replace the spars now than let it go for a lot longer. We are still having the eddy current being done. It's an issue in many of our regions where we don't have the suitable NDT technicians available, and the aircraft has to be either flown to somewhere where the NDT technician is available, or the NDT tech is flown into the site to carry out the inspections, and they're quite expensive, which has led to myself spending a fair amount of time trying to get sufficient data together to do the fatigue analysis and come up with something that's rational and reasonable. And just to answer Mal's question in the chat, what is the prognosis for Pawnees that have not had the spar replaced? The prognosis is ongoing inspections, um, aiming at doing visual inspections using a suitable inspection camera, somewhere in the order of every 500 to 1,000 hours at the wing root. Uh, Multiply that by 3 for areas mid-span and under the strut. It will require inspection panels to be added to the leading edge, under the underside of the leading edge, to be decided. Any other questions?
Sorry, Alan. One of the things I'm interested in about this AD is because it's kind of one of the rare times in which I think the AD actually makes the airplane more unsafe by doing it versus correcting an unsafe condition, which is removing those skin or those screws from the leading edge screws to be able to do the eddy current. Are you able to do the eddy current without the removal of the screws?
No. Um, if you're trying to do the eddy current on the inside, the screw will get in the way of the metal where you're trying to get between the screw and the spar cap, so that little area of the flange there. It's not a great outcome either way, which is why I wanted to go down the visual inspection path and try and leave the screws in situ, but still demonstrate that we had sufficient view of the spar flanges on both sides of the screw. With Sarah in the chat, why the inspections on the front spar of the spar? You need to have a look at the rib holes, in my opinion, on the front side of the spar. I think, in my personal opinion, the AD is insufficient. It does not include the rib holes. It does not include the rib holes on the front of the spar. And importantly, it's not looking at the higher stress region at the wing root. As I said before, I imagine that they've simply looked at areas where there have been troubles reported, but these troubles have been from premature cracking caused by leading edge screw holes that have been too close to each other or too close to the flange bulb or the spar cap joint. It's a little surprising that they had the failure in Colombia, again from a poorly drilled hole, but it came from that wing root area and it's not included in the inspections. My recommendation has been for the Australian Pawnees that if the clubs can afford it, it would be better off to replace the spars in total, and get away from all that agricultural history, and then have an aeroplane where the spars will last longer than any other component on the aeroplane. I acknowledge that many clubs do not have the financial wherewithal to achieve that. I have been suggesting very hard amongst Gliding Australia to either find federal or state government grants by which clubs could be subsidised. It's not big bickies with 2.25 million for 45 aircraft is about $50,000 per aircraft, that goes a long way for doing the spar replacement. 2.25 million Australian is not pocket change, but in terms of government spending and grant money, it's not big bickies either. So something along those lines would be of great benefit to clubs, and then end up with a Pawnee fleet that's pretty impervious to fatigue issues on the spars going into the future. I will suggest that there may be other problems occurring in the agricultural community with Pawnees that might result in other ADs, and given the what in my opinion is the deficiencies in the existing ADs, that we could see further issues arise from those ADs, not necessarily being well thought out.
Maybe you've already speak about this, but does the Australians already have a path forward? If you replace the spars, then you have longer inspection intervals. I understand you're doing coupon tests to potentially get
I'm
that, but currently not right now. If you replace your spars, you still have to do the very restrictive inspections, correct?
We have under the AD, we have 5 years grace period before the inspections start again. So that gives me a further 4.5 years or so before the first aircraft with replacement spars becomes due in Australia. So I'm focusing very much at the moment on the visual inspection regime in lieu of the eddy current, because that's what's currently hurting the majority of our operators, is the cost of the eddy current inspections. And I've got a little bit of time up my sleeve to do the spar replacement lifetime. That being said, once the fatigue analysis is completed the second time around, I'll probably start submitting what I would call trial AMOCs. CASA has already indicated to me they wanted to do AMOCs by aircraft, not as a batch. So this would be on a case by case basis. So I would start submitting individual applications for extension on individual aircraft. For the Australian audience, my proposal is to have Gliding Australia pay for these AMOCs initially, because the first few AMOCs are probably going to be more expensive for CASA to assess than some of the follow-on AMOCs. I strongly suspect that once CASA staff have done the first dozen or so applications for extension, they might get a little tired of doing it on a case-by-case basis and allow a group application to be made after they've got some confidence in what's going on. The then Gliding Australia would average out the cost and bill the individual operators, and that way the lead aircraft with the first submission is not paying extra, simply because of the additional administration time to sort things out. Anyone else? Oh, well, thank you, everyone. It's been an enjoyable webinar. I hope people got something out of it, and I'll keep people posted as developments happen. But everyone, have a good day.